The objective of this lab was to create a star trajectory specific to your email address and examine the data of a star's motion to calculate the net force acting on the star, and use that value to find the unknown mass of the black hole represented in the computational model. The main topics covered in this lab were the parallel and perpendicular components of net force and the universal law of gravitation. The rate of change of momentum has two components, one along the momentum, which is called the parallel component for obvious reasons, and one perpendicular to the momentum, called the perpendicular component. The equations for the calculations of these components are shown below. The universal law of gravitation is also displayed in this lab because we're using it to find the mass of the black hole, since we are already given the mass of a nearby star. By modifying the law of gravitation and its equation, more importantly, the mass of the black hole can be calculated using the equation shown here, which is the gravitational force times the magnitude of the displacement squared over the gravitational constant times the mass of the star. Before I explain the methods and results of this experiment, here is some background information on black holes. The presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation, such as visible light. Stars, passing too close to a supermassive black hole, can be shred into streamers that shine very brightly before being swallowed. If there are other stars orbiting a black hole, their orbits can be used to determine the black hole's mass and location. This concept and idea is pretty much the basis behind this experiment and how we plan on calculating the mass of the black hole in the lab. In this slide, you can see the code for the computational model I created to simulate the star's orbit around the black hole. As you see in the code above, the net force is calculated by dividing the change in momentum over the change in time. The parallel component of the net force is the total net force minus the parallel component of the net force, and vice versa, to calculate the parallel component of the net force. Then, the mass of the black hole is calculated by multiplying the magnitude of the net force by the magnitude of the distance from the star to the black hole squared, and dividing that by the product of the gravitational constant and the star's mass, just like in the equation from 2 slides before. As seen in the model, the light blue arrow represents the parallel component of the net force. The pink arrow represents the perpendicular component of the net force, while the orange arrow is the overall direction of the net force. The model also shows the calculated mass of the black hole at different points in the star's orbit. What I did was took all of these masses and put it into an Excel spreadsheet where the average of the cells of the input of all the masses were about 1.00 times 10 to the 34th. Now to look at a hypothetical situation. Imagine the black hole whose mass that I found was removed, and a different black hole was placed in that same location. If we're assuming that the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole, would it be possible for me to find a value for the mass of the new black hole, which is different from the mass we calculated for the previous one? Well, since in this situation the position values are the same as before, the magnitude of the distance between the star and the black hole is still the same value, or the same magnitude. Therefore, the velocity, the momentum, and the net force are not changing, which means that the same equation for calculating the mass of the black hole can be used in this situation with the same values, which means that we will not get a newly calculated value for the mass of the black hole, and it will be the same as the one calculated to the previous situation.